Okay, so thank you for joining us in this briefing. This is Back to the Future with Platform Security, and my name is Enrique Nissim. Here we're with Krzysztof, Okupski, and Joseph Tartaro. We work at IO Active. We are data security consultants, where we work a lot of low-level code review, reverse engineering, and specialized tooling development and hardware as well. So, this presentation is going to be focused on AMD. We have a pretty packed outline, as you can see, but we're going to be talking about SMM protections, SPI Flash configuration, some SMI handlers, ROM Armor, which is a technology specific to AMD, platform secure boot, which is the Intel boot guard equivalent, and SMM Supervisor, some isolation technology. So how this research started? Back in 2021, we acquired an Asus Ryzen gaming laptop, and naturally we passed some SMI handlers in there, and the system completely hung. And so we started digging, okay, what was going on there, right? We tried running CHIPSEC, and it failed dumping the SPI Flash. And we realized, okay, yeah, has minimum AMD support. And after digging into it, we started asking ourselves some questions. So, what are the registers used to protect SMRAM? What about the SPI Flash? How about hardware secure boot? All these things that CHIPSEC already gives you when you run it, right? We stumbled upon the fact that there's not a lot of research around AMD, and also the documentation. It's a problem. Documentation from AMD, for some reason, is only available for some of the families of the processors. AMD stopped publishing this document, which was very useful, called BKDG, the BIOS Kernel Development Guide, for newer models. I think the latest revision was from 2016. And also, there were some inconsistencies across different documents. So you have the programming manual saying something, and then the PPR, the processor programming references, saying other stuff. And also on top of that, many of the interesting documents are on the NDA. So technologies such as platform secure boot or PSB ROM Armor are only available to OEMs, the details of how those work. So with that said, all the information that we're going to provide here was obtained through reverse engineering and black box testing. We did not have an NDA with AMD, and because of that, there could be some inaccuracies in our conclusions, but we did find a bunch of bugs and issues, so I hope you enjoyed the whole thing. Starting with SMM configuration. For those not familiarized with it, what is SMM, right? SMM is this very privileged, the most privileged execution mode in x86 processors. It's what's called ring -2, and it lives in this area of memory called SMRAM. SMRAM must be protected in a way that the hypervisor or the OS cannot tamper with that memory. And the hypervisor and or the OS can communicate with it via what's called system management interrupt, software system management interrupt. So, triggering an SMI in Intel, which is what CHIPSEC does, it just writes to an IO port. The IO port is hard-coded to D2, and if you just randomly get an AMD laptop and you run CHIPSEC, there's highly likely that they are not going to be hitting anything, because in AMD the configuration works differently. There are two ports in the power management controller configuration that has to be reviewed before. The default is to be 0, so that's important. You have to probably write to be 0 or check that those ports before. About the SMRAM protection, there are two possible SMRAM locations. One is called the TSEG, which is the equivalent of Intel CSEG compatibility segment. That's the video memory. But that's for all the models. We haven't seen any model really using that. Normally, it's used what's called a TSEG, top of segment memory. But essentially, it is configured with these registers. And yeah, we have a TSEG base and a TSEG mask, which together they define the length, the date, and the length of the entire region that is where SMM code is going to live. And then we have SMM base. We have each one of these MSRs is per processor. So we have an SMM base per processor. And finally, we have an SMM lock, which, if set, it prevents this other register to be modified. So this is important. This has to be set so the OS or the hypervisor cannot modify it, the TSEG base, the mask, and disable the protection and then tamper with it. And of course, when we read about this, CHIPSEC, when you run it, already gives you a lot of information of what is well configured and what is not well configured. So we implemented something similar in our tool called Flatbox, and we found immediately a bug on an Acer Swift 3 where this SMM log was not set, which of course gave us the ability to modify SMRAM and get SMM code execution. There's a blog about it with more details. But continuing with other interesting features that are present in SMM, we found an SMM lock feature, which is interesting. I said before, the SMM lock has to be set, and the idea is that when you set that, it's only going to be cleared once you do a reset of the system, power cycle, right? But with this MSR, you can configure a sort of password where when you put it again at runtime, then that protection is cleared and you get access again to configure the whole TSEG region. We don't know why this feature exists. I don't know if an OEM uses it. In all the laptops that we evaluated, it was not used. But still, it's interesting because as an attacker, we can abuse this functionality, and we're going to show later how. About callout protections. What is a callout? Essentially, this happens, it's a condition that happens when SMM, for some reason, a vulnerability, most likely, ends up executing code outside of the TSEG region. So, because we can tamper with the memory outside of TSEG, we can then, of course, get SMM code execution. In Intel, we have a feature called MSR SMM feature control, which is, when this is configured, it prevents the processor from fetching instructions from outside the TSEG region while on SMM. So that's good. That prevents a lot of easy callout exploits from working. From AMD, in the case of AMD, there's no such register, so no similar protection, which means that a bug that could be, not exploitable in Intel, it's easily exploitable in AMD, depending on paging, of course. Yeah. Let's talk about SPI Flash configuration. We have two access modes to SPI Flash. We have direct memory mapped I/O, and we also have index mode where we send opcodes directly to the SPI controller. And we have protection for both of them. We have ROM Protected Ranges and SPI Restricted Commands. So ROM Protected Ranges are registers that are configured so that we cannot write or read, depending on the attributes of registers, into the flash, even if we are on SMM. That's the idea, at least. The thing is, well, for people that is aware of how Intel works in this area, Intel have what's called a programming range registers, and those work very well in that sense. You cannot tamper with the flash even if you are in SMM. However, in AMD, you can reprogram these registers, so it's kind of curious. Yeah, we found even in systems where it was completely switched off, we could not even write from the OS. So if someone actually has more information about why that happened, please talk to us later. It's interesting. But this is how it looks. It's similar to the protected range registers in Intel. When the range is well configured, you have like you can see a particular base size and some attributes in there to prevent reading or writing. Reading works well. So, and the SPI restricted commands are we can map the SPI controller and send opcodes directly to the SPI controller and do what the SPI vendor allows us to do, like depending on the chip, right? Window, for instance. And we can read, write, erase. That's the basic commands. And there are some, of course, the firmware has to program a register to protect from the OS sending these commands directly. The firmware has to protect itself from the runtime, right? So if we get to see how the SPI Flash has to be configured, well, we have a couple of things that we need to do. We need to program the ROM Protected Ranges, program the SPI Restricted Commands, lock them, enable the protected registers, and unlock the ROM Protected Registers as well. So it's a bunch of steps, and of course, we saw some vendors doing it wrong. So this is a Lenovo ThinkPad P16S, the AMD one, and we can see how they are not restricted opcode in that list, which means from the OS, we can just write directly to the cycle, to the flash. How does that work? This is a case with reading. Basically, these are the different registers from the SPI controller, and we first program the opcode that we want. This is, in this case, it's read. We put the 13 in there. Read. We program the byte count, the RX byte count, the address that we want to read from in the flash, and then finally we hit go, and the result is that green area highlighted in there. And this is another example. This is a Q4 PC, TravelMate B414, and in this case, we have the same issue. So we're going to be sending a message to David Weston. Right there, we can see how this is programmed. This is proof of concept reading based on the library that we referenced before, the Flatbox tool. Tartaro. So first, we found a page that it can be written, and then we write the message. And this is one of the few memes we have for this presentation is saying, wait a minute, Duisel. Are you telling me that we can just write to SPI Flash in Secure 4 PC? And yeah, so. And that's a newer model, but this older gaming laptop had the same issue, and it was, of course, ASUS. We reported this to ASUS. They informed to AMI, and we're still waiting for the fix. This happened December last year. They don't seem to be doing any progress in there. Yep. So, all right.
So far we have seen that the security of the SPI Flash largely relies on the security of SMM, right? So if we manage to compromise SMM, we can therefore compromise the SPI Flash. But we thought, okay, so we have seen all these misconfigurations that we can abuse from the operating system. What about actually SMM code? I mean, we could try to exploit like typical SMM issues, like memory corruption issues, but that's not really interesting. So we tried to find modules related to the SPI Flash, and we actually found a couple of interesting examples that basically all the work for us. So, for instance, we have found specifically two modules, which are partially censored in this case. One from the LCD, the second one that's independent. And in this presentation, we just want to focus on the second one. It's a very curious example. So, the story begins with the firmware block services, which is the verified IDE inside. And those who watched maybe Microsoft talks about supply chain attack issues, well, you'll know that basically you have one IDE which provides code that ends up in various systems, right? So one IDE can provide, for example, code for 3, 4, 5 different OEMs, or even more. And this is the case here as well. And we found that this module exposes three very interesting operations, which honestly it should. So SPI Read, Write, and Erase. So essentially from the operating system, we can directly go into the SMM module, and we can do any modifications to the SPI Flash. Pretty bad, right? I mean, thinking already about what we can do there is, hey, we can write that DRAM region where we have the variables with, so we can switch off secure boot, for instance. Very nice if you want to, for example, develop a bootkit. Very handy. And you can also try to maybe override other regions where the code is, but that's where the hardware will frustrate you here. So we wanted to inspect a little bit more how these modules work for read, write, erasing the SPI Flash. So we took a look at those, and we found that, for example, the read is basically just a mem copy behind the scenes because it's running on mem.io. So here we see that it actually calls into SPI Read, which behind the curtain is called a mem copy. Simple enough, right? Just copies from its address. And then the write, for example, goes over indexed mode that we get these images now. And we wanted to see, okay, these modules, we want to proper checks, can we do something more with that? And we saw that actually in this handler for the SPI Read, there were no checks whatsoever. So you can see over here, essentially all three parameters, which are the source address, destination address, and the site, they are basically fully controlled heads. So fully controlled mem copy, we all know what it means, it's basically a mem, right? So at that point we thought, okay, let's exploit this, but right when we thought we hit gold, there's something that we missed, actually. You can see over here there is a flag called Disabled Firmware Block Services in my handle flag. We call it like that, but essentially this flag is set when, during the boot process, an event is triggered, specifically the EFI event legacy boot, and that event essentially at the end of the Dixie phase, it locks down the interface. So we cannot do anything at the runtime of this anymore. Well, bad luck, right? So we kept on digging, looking for other modules related to the SPI Flash, and we actually found another one here, partially censored, and it's called runtime Dixie. And we saw that actually it exposes an SMI handler as well, and it proxies all of our commands back to the previous module. So we're back in business. And we can see over here all the arguments are fully controlled because they are passed by us from the operating system by the communication buffer. So once again, we control source, destination, and size. So we wanted to get our hands dirty and try to exploit this. It's relatively straightforward. We did a bit of reversing to see what exactly the structure looks like, how to fill it out, and we saw, okay, source address is simply a pointer. We will control it. The size, we will control it as well. The destination buffer is actually the end of the communication buffer that you pass as a command to the SMI handler. So we implicitly control it by aligning the communication buffer to a different position of memory. So how can we abuse this? Well, we can get an arbitrary read, quite simply by making the source pointer point to the beginning of a TSEG region, for instance. And we can, like that, all of TSEG. So we have a nice leak. That's a nice primitive already. But we can also turn this into a write primitive by just simply aligning the communication buffer to the beginning of the TSEG region and making the source point to our payload that we want to write. And because we have the arbitrary read from before and we can have a full dump of SMRAM, we can just simply use the previous leak, modify portions of SMRAM, and then write them back into the TSEG region. And basically we overwrite SMM codes, so it's already game over. Here we can see a very simple POC of the leak where we simply read the beginning of TSEG. You'll see that basically almost always the beginning of TSEG, at the beginning of TSEG you're going to have a structure which is called SMM S3, which is a typical structure for S3 sleep functionality. So when we leave TSEG and we see this magic at the beginning of it here at offset X28, we know that we were successful. So we dump off SMRAM, we actually try to analyze it for good exploitation, and we found that there is a tool from Dimitri Oleksiuk, but it only works on Intel, so we've done some tweaking. We have published an updated version of it, so it works on AMD as well. And with that, we can see, for example, all of the SMI handlers which are registered, so we know which SMM modules are loaded, we know which SMI handlers are registered, and we can, and afterwards, just simply go through the modules one by one and check, for example, for issues in all of them. So, for analysis purposes, very nice. Okay. So far we have seen that the spike can be compromised from the operating system, with misconfigurations, or for example, via exposed SMI handlers, just like we saw now, or really any kind of SMM privilege escalation issue, because we know that if we get code execution in SMM, we can reprogram the SPI protections as we want. So to resolve this, AMD came up with PSB ROM Armor, which effectively, like Enrique mentioned, it's the equivalent of Intel's Protected Range registers. And it's supposed to stop attacks that target SMM. So what it does essentially is when this feature is configured, you're not allowed to send write transactions to the SPI Flash controller anymore from the host CPU. Actually, what it does is it requires the host CPU to go to the PSP, and the PSP, for those maybe that are familiar with it, is an embedded CPU within your AMD CPU that will do the gatekeeping at this stage. So essentially what's going to happen is, if we want to talk to the SPI Flash, or at least to write to the SPI Flash, we have to go send a transaction request to the PSP, and the PSP will do it for us. So here we can see, if we go from the operating system, denied. If we go from SMM, denied as well. So essentially, PSP is going to be playing the role of the gatekeeper now. So we try to understand how the PSP is configured, what are the allowed ranges. So we saw that in the PSP directory, which is a data structure on the SPI Flash, there is a policy, which is embedded at build time, which defines the list of whitelisted regions. And essentially when the system boots, that directory, the entries in the directory are read, and PSB ROM Armor is configured. So in theory, the only writable regions should be the DRAM regions, because those are the only ones at the runtime where you might do some modifications. So your UFT variables are the ones that you want to modify, but anything beyond that should be actually locked out. And we have created a script to parse the PSP directory and extend these entries. So here we can see, for instance, on the Acer Secure Core PC, we are actually extracting these entries, and only a very small portion is whitelisted, which is the NVRAM region. So we wanted to dig a little bit deeper and understand exactly what the interface with the PSP is for this feature. And there are essentially three main steps. One is the init step, then we have the registration of an SMM interface, or interfacing with the SPI Flash for other SMM modules. And finally we have an SMI handler, which is for supposed to be only used by Dixie drivers at boot time. So during the init, there are two things that are being done. One is enforcing SMM only mode, and the second step is just basically sending a bit of information information to the PSP about the SMM region. And that's pretty much it. So we try to understand, okay, what are the structures that we just into the PSP, and we have reversed that part, and we saw, okay, the read is done by AmdPspRomArmor3Smm, so we can just simply do that from the OS actually, it doesn't really matter. The critical part is the write. So we reverse the structure, and we know exactly what kind of structure we have to send to the PSP in order to maybe leverage this feature. And at that stage we thought, okay, I mean, talking to the PSP, it's a simple mailbox and doorbell mechanism. So we take the structure I've just shown, we put it in the mailbox, we ring the doorbell, and it should perform the transaction for us, right? And by doing so, we can potentially bypass SMM. But there was one step that we missed out, and that was that actually the SMM only mode enforces, rather, how SMM only mode enforces that you cannot actually do that. So there's a trick to that. Every time that you send a transaction to the PSP, what happens is it's going to check whether a flag that only lives in SMRAM memory, which is protected, is actually set. It's called the SMM flag, and essentially SMM code, every time it performs this transaction, is going to set it to true. And when it finishes the transaction, it's going to switch it off again. And since we cannot, from the operating system, touch this piece of memory, we cannot just simply bypass SMM altogether. So those were the first two parts of this SMM module, and the third part was that we had this SMI handler, right, which was exposed to Dixie module. So that was marked red, and I'm going to explain now why. So it exposes various functions, this SMI handler, like SPI read, write, erase, which in itself is potentially dangerous. And it actually likes all kinds of validations as well. Once again, we can pass basically arbitrary buffers because the validation isn't done properly, like the size of the buffer that is validated is actually like a control, and a minimum size is not enforced, so we can tell it, hey, the buffer is on this size, but actually we're going to read or write to a buffer which is way bigger, so we have broken bounds checks. We can try overwriting portions of the SPI Flash, but there was this one function that we actually mentioned before, right, for the deregistration of the handler. And we thought, okay, well, if it's registered early enough, then we can attach it from the operating system. And that's where we found actually it's deregistered too late. So typically, these types of handlers should be deregistered at the end of the Dixie phase, when also all of the important security features for a platform are locked down. But this is not done over here. Essentially, it's done one stage too late. It's done at the end of the PDS phase. Essentially, when execute services, the execute services event is triggered. And essentially what this means is, well, at the end of Dixie is where essentially the security boundary lies. Because that's when all the lockdown happens, and that's when the handover to potentially untrusted code happens as well. So for instance, in the BDS phase, I can run a UEFI shell, which is potentially signed. Or for instance, if you have a secure boot bypass of some kind, that we have seen actually quite a few examples in the wild, which are still exploitable. Essentially, you can run code early enough, so if your secure boot system is broken, if you run code early enough, you can actually execute code in BDS. And if you can do that, you can abuse these issues still. And we have found that this is actually part of an AMD module, which is used across different vendors, and once again, hasn't been fixed. So to recap, I mean, we have covered a lot of issues, right, that we can have with SMM, with SPI protections. We have found bugs which are quite dangerous because we only approach escalation to SMM. We can write to the SPI Flash on basically all the models we have tested, which is pretty bad. But then we thought, well, what's the one thing that we are really missing, right? So the issues that we're exploiting right now, we did this in a runtime, and basically when we reboot the system, well, we back to square one. So what about persistence? That's the holy grail for attackers, right? So this is really the topic of platform secure boot. So platform secure boot is hardware of trust developed by AMD. It's provided by the PSP, and it verifies the second PI phase, which are the very first parts of the firmware code. And later stages are basically verified by custom code implemented by OEMs. But in this step, we're only going to focus on potential configuration issues. So let's take a look at the high level how this works. So in the first step, when vendor wants to implement a secure boot, what they do is, well, they first create a key and then let AMD sign it. And the second step, the BIOS is compiled in several different volumes are created. One is the PI volume. Then we also have the volumes for later series of the Dixie volumes and the BIOS and DRAM. Then in the third step, the PSP directory is created. So the PSP directory is just a directory of different kinds of entries. It's going to have pointers to things like various components of the PSP. It's going to have pointers to the PI volume, to the BIOS signing key, and also, for example, entries for the PSB ROM Armor. So it's basically like a reference, like a content for different kinds of data structures in this file. Then in the fourth step, you sign the PI volume, and in the fifth step, you combine it all together and you turn it into one image. Right, so at that stage, we had a high-level understanding of what happens during the manufacturing process. But we wanted to understand, okay, when we have a system, how can we actually evaluate whether this was done properly? So we've done some reversing of these PI modules, which are running in these early boot stages. And we found one PI module which was very interesting because it was interfacing with the PSP and it was used for configuring the PSB. So we found that basically by writing a specific constant to an index register of 0 device 0 function 0, essentially by writing a specific offset constant over there, we can get the PSB MMIO base address. And by getting the base address basically from there at certain offsets, we had configuration registers for the PSB. So that was very interesting to us, and luckily enough, the vendor from which we extracted this PI module also had lots of nice prints, so we understood exactly what the structure looked like. And there are two registers which are really of interest to us related to the PSB. One is the PSB Fuse Register, which reflects the PSB Fuse configuration, and the PSB Status Register. So the PSB Fuse Register is pretty self-explanatory. It has a couple of fields like vendor ID, model ID, etc. But the two fields which are really interesting to us are the PSB enable bit and the customer kilo. If these two bits are set, then we know PSB is enabled. So our trust should be fine. And then also the second register is the PSB Status Register. There's only one field that we are really interested in, which is the PSB Status field. And that one essentially indicates, well, if it's 0, then it's all fine. If it's a non-zero value, like 01 or hex22, which we've seen a couple of times, that means that basically the system doesn't really have PSB properly enabled. So a system which has PSB properly enabled looks like this. Like the Novatek P16S. We can see that the vendor ID is set, the PSB enabled bit is set, and the customer keylog, which logs down the use state, is also set. And we also see that the status is actually 00. So the system booted, it was all verified properly, and everybody was happy. But we have seen quite a few systems where this configuration wasn't applied at all. And this is just one example of this, in ASUS 3, where we saw the fuses weren't set at all, and the status was returning 01. So that's actually we thought, I think we found what we were looking for, right? So, using these issues that we have mentioned before, we went ahead and we implemented a modified version of a firmware volume. We have modified a little bit to implement our backdoor. And what we have done is essentially what Enrique mentioned in the very beginning is we are going to use the SMM key to disable all the TSEG protections. So here we can see that the HWCR bit was set, like the last bit was set, the SMM log, and that the TSEG protection is also enabled because you can see actually in the SMM mask it ends in 03, so the last two bits are set as well. So SMM protections are properly enabled. So we just put in IO active and hex, and we see what happens. Well, the SMM log is still set to 1. Well, no luck. Well, then we run our exploit, which just overrides parts of the SPI Flash, which we have modified for the backdoor. This takes a little while, 2 minutes. I'm just gonna go and skip forward a little bit. This part, the system reboots. There we go. Again. So essentially, we have overwritten parts of the SPI Flash with our malicious code. System boots again. It's already a good sign. Because break actually quite a few aspects of the process after we pull on the SPI Flash, but this one is fine. And we see over here again, we're gonna perform the same steps as before. We are gonna enter the SMM key, which is not supposed to be configured. We're gonna input and let them once again, and we're gonna see what happens to the SMM block when we use WC on. So we put in the key, and we are gonna see in just a second. Well, we're going to see that the SMM log bit and the HWCR is going to be set to 0 now, meaning that all the logs of the TSEG protections are disabled. Yeah, and now we can set the TSEG protection back to 0, and boom, it's disabled. And here we can see on the left side that actually we have read and write access now to the TSEG region, which was all as before. So by doing so, we have persistence and ring -2 on the system. All right. Sure.
Cool. So let's talk a little bit about the AMD SMM Supervisor. So what is this? Intel had this technology that essentially failed called the System Transfer Monitors, the STM, and for years everyone waited for a reference implementation that just never came out, and it's also just a really complex technology. But we know that SMM is just too powerful to have without something like the STM, because we need to have certain security guarantees. So the industry went with a different direction. Intel has the Intel hardware shields, AMD has the AMD Supervisor, and Microsoft has Project Mu. And a good friend of ours, Ilya von Sprundel, gave a presentation called Assessing the Security of an SMM Supervisor at the last hardwear.io. And that was essentially him performing a code review and analysis of Project Mu, and kind of reporting on some vulnerabilities he found and analysis. So you should definitely check that out. So quickly looking at the Project Mu GitHub page, it's kind of interesting. They describe it as refactored from Tiana Core common modules and public portion of the AMD SMM Supervisor. This is funny because there is no public portion of the AMD SMM Supervisor. So this essentially became our public portion. So you should go check out the GitHub repo. And just from like a high-level perspective of once this supervisor is running, you now have your SMI handlers, and anytime they want to access something like an MSR or an IO register, it's now going to have to go through an enforcement module. And that module will go ahead and validate the request against some sort of OEM policy and see if that is allowed or not. And they also implement paging. So now once it has to access the system memory, it has to deal with paging. So if you want to look at some of this, the SMM Supervisor lives inside of the SMM Supervisor bin release binary. That's inside of your BIOS update packages, and that's the GUID for reference. And associated with it is a freeform blob called the SmmSupvBin. And that is what contains the OEM policies, the new trusted SMM entry code, and other things. And that's the GUID for your reference as well. So from a very high level, just kind of walk through of the initialization and what it does at runtime. The SMM Supervisor in the middle, you can see that's running under CPL 0. That's essentially a new operating system running under SMM. And the first thing it's going to do is it's going to read out from SPI Flash that SmmSupvBin binary I talked about. And it's going to obtain the OEM policy. It's going to grab the new trusted SMM entry code. It's then going to issue a request to the DRTM trusted application running on the PSP. And that's it basically handing off what it got from Flash so that the PSP can hold on to it for the future. Once that's done, it will have a registered interface that this PI SMM CPU Dixie module that's going to reach out to it. And what that interface does is it will hand it the new SMM entry code that it will then copy to the SMM base at offset x8000. So now this new entry code is living there. Every time an SMI is going to happen, that's going to trigger. It's going to perform its standard initialization, 16-bit to 32-bit to 64-bit mode, verify that the supervisor is initialized and running, and if everything's good, it will pass control back to the supervisor. Now, once the supervisor is running, it will then reach out to the PSP again. And remember, this is going to happen every single time an SMI happens, so every time an interrupt, it will reach out to the PSP to obtain the original data that is sent to it. So the OEM policy, the SMM entry code, portions of SMRAM, all those things are going to be verified each time. This is to check if an attacker has some sort of bug and was able to corrupt SMRAM or modify the new entry code. It ensures that it has not been modified. If all is good, everything passes, it will now deprivilege itself. It's going to call into the SMI rendezvous block, which is running in CPL3, and that is now going to continue execution to all of your normal OEM SMI handlers. So now you'll see that is essentially the isolation and the deprivileged portion. So all the handlers are now running under CPL3, and if they ever need to do any sort of privileged process, they now communicate through a new syscall interface to the supervisor. So this is an example of a demoted SMI handler. You see the very first thing it does is it will check the CPL. If it's at 3, then it knows that the supervisor is running. It's deprivileged, so it's going to call into the syscall interface. But if it's not, if it's running a CPL 0, it's going to go ahead and execute its normal, SMI code. And in this case, just doing like a read MSR. So the code is still going to exist for legacy purposes, or in case the supervisor is not actually initialized. But essentially, when you see that branch, that's what you're looking at. So, really quick, just kind of going over quote-unquote legacy supervisor syscalls. The reason we refer to them as legacy is because that's what Project Move refers to it as. And that's because Microsoft implemented a large number of other syscalls. Like you can do things like register new SMI handlers and such. But in terms of the legacy ones, you can see comparing Project Move to AMD, the first 7 are exactly the same. You can do things like read MSR, write MSR, read and write IO registers, etc. And then AMD has 2 additional ones, and this is the supervisor read and supervisor write. And this is for specifically reading and writing to PSP. So you'll see that there's a range of approved registers for reading, and then for writing there's a subsection that's in red, and those are the registers that are restricted from writing to. We're not sure what they are, but just so you know. In addition, like I said, it's a full new OS. They implement paging, so they protect things like the GDT and IDT and everything. So all of those can only be accessible to CPL 0 now. And in addition, they also lock CR3. So an attacker is unable to modify the base address of the page table. So, in terms of attack surface, it has all of your standard operating system attack surface, your interrupt handlers, the syscall interface we described, the PSP communication, the back and forth, and those OEM policies that we described earlier. Now, in terms of just for time and for this presentation, we're only going to cover OEM policies. So, going back to the SmmSupvBin file that I mentioned, it has a very basic format. You'll see that it has a magic $PSP at the start, and it will have a table count. So in this case, this table has 5 entries. So you'll see the start is a type, then you'll have a length. So this type C0 is a length of x200, and it's at offset x400 of this binary. So walking that table, you can see we have 5 types here. C0, C2, and C3 are unknown to us. Looking at their size and what it looks like, we're just under the assumption that it's some sort of signature, maybe certificate. It makes sense that it's something like that because you would expect the trusted SMM entry code to likely be signed and probably get verified by the PSB. But in terms of Type C1, that's the new trusted SMM entry code, and Type C4 is your OEM supervisor policy. So, going back to Project New, when analyzing all this, it became clear that it's essentially a fork of the AMD code. So when we were reverse engineering the modules, we had the Project New GitHub open and just kind of comparing. And when we got to certain features, in this case the OEM policy stuff, a lot of the functions were actually one-to-one matches. So this obviously made our lives significantly easier and gave us a lot of context. Because if you were to go grab that binary file from your package and extract the OEM policy, you'd be looking at this. And what the hell is this, right? None of it doesn't give you any context. You don't know what any of it means. But Project New to the rescue. You just go to the GitHub repo. You have nice, detailed, commented structures, and now we can actually understand all this and parse it. So, just kind of going over analysis of these OEM policies. What do they allow the OEM to do? They essentially allow you to implement either a blacklist or a whitelist. You can choose, and then they allow you to do that against certain features. So in this case, they're forming a blacklist against 2 I/O registers. They're restricting the right to CF8 and CFC. So they're essentially blocking you from the PCI configuration space, which makes a lot of sense. It should do that. In addition, this would be the vendor performing a blacklist against a large number of MSRs. And in addition to that, they also allow you to either block or allow certain instructions, such as clearing interrupts, faults, things like that. And you'll have the subsection for denying of memory access. So when analyzing a bunch of the policies, this memory access section was always blank, empty. And that's because it's just the static policy. But it actually gets updated with the paging. So during runtime, that's going to be changing. So if you see an empty one, if you decide to dump your own and look at it, that is why. Now, in terms of kind of analysis and comparing across vendors, one thing that was interesting is we saw some vendors were actually blocking these 3 MSRs in addition to the other list we showed. And we're not sure what they are, but it kind of raises some questions. Are these something that an attacker can take advantage of to get a foothold on the system? So if you grab a machine and you don't have these blocked, are you potentially vulnerable to something? We don't know, but it's interesting because we think this is probably going to be the kind of the methodology moving forward. Grab a BIOS update, unpack it, grab it, parse all the policies and do comparisons and see, hey, from a baseline, did they make a configuration mistake, right? And in addition, just looking at what's been blocked, we were kind of discussing, well, is there anything that they're potentially missing? So there's the FS space, the GS space, and the kernel GS space. And we thought those were interesting because, once again, you find a bug in some sort of OEM SMI, you exploit it, you have code execution under CPL3, we issue a syscall to write to one of these MSRs, then we issue another syscall or something that, the supervisor runs. Well, if it happens to use FS or GS, that might alter the code flow. The attacker may have impacted the supervisor in some sort of way, right? Another thing that was interesting is looking at the syscall for the reading and writing of the PSP registers. The PSP mailbox is completely unrestricted. So if you are that attacker in CPL3, you have full access to that for reading and writing, and that potentially allows you to attack the supervisor. At least we consider that attack surface. It's a question at least to investigate. So just some quick conclusions in terms of our research. We've reported 20 plus issues and counting. They affected AMD modules and different independent BIOS vendors like AMI, Inside, etc., and a bunch of different OEMs. Now, one thing that's just kind of an interesting observation is that it's clear that the OEMs are just failing to secure these platforms. AMD is providing the features for them to do it, but they're just failing to. Most of the issues we reported can actually be fixed with just a simple configuration change. It's not splitting the atom or anything crazy, right? The reason for this maybe will be that, independent security researchers are primarily focusing on Intel, so it's just kind of going unnoticed. But I don't really like that because it implies that an OEM needs independent researchers to tell them how to do something where we shouldn't, right? And then AMD also, as was mentioned earlier in the presentation, they've kind of implemented this policy of NDAs across all their documentation now. And this is an issue because security researchers can't easily grab documentation, figure out how a system should be configured. OEMs can't compare things. They can't look at what a competitor is doing. I really do think hiding behind NDAs is a net negative. But overall, we do think the industry is kind of moving towards a positive direction. Isolating SMM, deprivileging all the crappy OEM code is all good things, right? And we do think that Microsoft System Guard, Secure Launch, things like that are probably going to be the default soon. So this is kind of a positive note. But just kind of a quick call to action. As you saw, a lot of the stuff we were doing was with a utility we wrote called Platbox. It's available on the IO Active GitHub. And just if you have an AMD machine, just run our tool and kind of look at your configuration, share the results. If there's anything interesting that you think you found, we'd like to see it. But we will be pushing out some updates maybe today or tomorrow, just some new features and other things that we covered here. So yeah, and that's pretty much it. So we're open for questions. The three of us will be here over the next few days.
Okay, thank you. We'll take questions. Yeah.
My name is Thomas Penn, and I'm the founding member of AMD PSP. 11 years ago, I wrote the first code of PSP and designed it. And also, I'm later promoted, and I manage the entire PSP team and security in AMD. It's very interesting to see my own work being attacked, to be honest. And you can Google me in the LinkedIn, so I'm not BSing here. Okay. First of all, some of the things that you talk about is actually designed by me and my team, like ROM Armor, V2, V3, DRTM, TA, Platform Secure Boot. Actually, I designed that, and it was later on called ASP, right? AMD Secure Boot. I think majority of things you are right. Like ROM Armor, they didn't do ROM Armor V3, and also if you enable memory integrity, they won't allow you to go outside of TSEG, right? So all in all, I think that's very interesting work, and maybe later on we can partner together to give a tech talk later on in the next hardwear.io, and you can contact me. Okay?
Thank you.
Thank you.